Hi guys.
Hi Dishani.
Do you mind if I join you?
Yeah, sure. Please have a seat.
So, how have you been? Thanks, I'm good. I was just trying to catch up on some thermodynamic revision. It's getting tricky though. I was reading about refrigerator and heat pumps and I got a bit confused.
Oh, you are not alone. I just went over that topic too. It's all connected with the Carnot cycle, right?
Yes, I did some revision too. This topic is all about
The second law is used to determine the direction of a process. For example, a hot cup of coffee on a table cools down over time. Heat leaves the coffee and flows into the air. The reverse doesn't happen. Heat doesn't flow from cooler air back into the coffee. This shows that natural processes move in one direction. The second law also tells us that energy has quality, not just quantity. It helps us to understand how energy becomes less useful during a process. When the coffee cools, the energy it gives off becomes low-quality heat in the surroundings, which is harder to reuse. The second law is also used to find theoretical limits for machines like engines and refrigerators, and to predict how far chemical reactions can go. Lastly, a thermal energy reservoir is a body with a large heat capacity. It can absorb or supply heat without changing temperature, such as oceans, lakes, rivers, and the atmospheric air are examples of thermal reservoir because of their large thermal masses.
Before refrigeration, keeping food fresh was a pretty tough job in those days. People used salt in their food or bury in the snow to keep it fresh. But now the refrigerator has changed the way we conduct our daily life, making it easier to preserve food. Have you ever wondered how a refrigerator keeps your food fresh? Let's find out. Refrigeration is actually quite simple to understand the principle behind it. Just remember that when liquid evaporates, it absorbs heat, and when it condenses, it releases heat. As simple example is that even when your hand is wet, it feels cold. This is the process of the water evaporating and cooling your hand on a very humid hot day. Outside of the bottle, this warm your beer to pull off this frosty feet. A refrigerator uses 5 major components: an expansion device of evaporator coils, a compressor, condenser coils, and a refrigerant. The refrigerant is a liquid that enters in the expansion device. As it passes through the sudden drop pressure, make it expand, cool, and turn into gas. As the refrigerant flow around the evaporator coil, it absorbs and removes heat from the food. Inside the compressor, squeeze the refrigerant, raising its temperature and pressure. It's now a hot, high-pressure gas. The refrigerant then flows through condenser coils and on the back of the fridge, radiating its heat to the atmosphere, then re-enter the expansion device, and the cycle repeats itself. So basically, heat is constantly picked up from the inside of the refrigerator and taken outside of it.
This animation illustrates how a heat pump operates. Generally speaking, a heat pump transfers heat from the air in the room to the water in the tank with the aid of a substance called a refrigerant. As it cycles through the system, the refrigerant undergoes variations in temperature and pressure, as well as alternating between liquid and vaporous states. Let's examine the 4 stages in one complete cycle. In the beginning of cycle, the refrigerant is in a cold, low pressure liquid gases state, flowing through tubes that are exposed to room air. It is colder than room air, so the heat in the air moves to the refrigerant. This is because heat wants to move from warmer things to cooler things. To facilitate the heat transfer, the tubes are connected to an evaporator, a heat exchanger, much like a car radiator, with many fins designed to increase the absorption of heat from the warm air into the cold refrigerant. A fan amplifies the absorption by increasing the flow of room air over the evaporator. The heat added to the refrigerant causes its temperature to rise and the fluid to become a warm, low-pressure vapor. As the refrigerant changes from a liquid to gas, large amount of energy transfer takes place. Once it's passed through the evaporator, the refrigerant is a warm gas, the cold liquid having been warmed and vaporized by the room air. The refrigerant still not hot enough to heat water, however, so that's where the compressor comes in. The compressor raises the pressure of the gas, which also raises its temperature. Once it's hot enough, the heat will flow from the refrigerant to the water. The compressor next forces the now high temperature, high press gas further along the cycle into another heat exchanger called the condenser. The condenser is in contact with the water and the hot gas now gives up its heat to the colder water. As heat leaves the gas refrigerant, it cools off below its condensation point and changes from a gaseous state to a high-pressed liquid state. The change from gas to liquid facilitates the large transfer of heat energy to the water. Finally, the now cooler high-pressed liquid refrigerant passes through an expansion valve. As the refrigerant passes through the valve, its pressure and temperature are greatly reduced, now cold and in a vapor state. The refrigerant is once again ready to absorb heat from the room air and repeat the cycle.
A car engine with a power output of 65 horsepower has thermal efficiency of 24%. Determine the fuel consumption rate of this car if the fuel has a heating value of 19,000 British thermal unit. That is 19,000 British thermal unit of energy is released for each IBM of fuel burned. As the analysis of this question, a schematic of the car engine is given in figure 6.17. The car engine is powered by converting 24% of the chemical energy released during the combustion process to work. The amount of energy input required to produce a power output of 65 horsepower is determined from the definition of thermal efficiency to be using the formula of thermal efficiency dip. So, to solve this, we need to use the formula of thermal efficiency definition. Firstly, we need to substitute the value of 65 horsepower in the power output and divide with 0.24, which is thermal efficiency. We get the 0.24 value by dividing 24% with 100 to get the decimal place. And then, with the value, we need to multiply with 2545 to convert horsepower to British thermal unit. And we will get 689.270 British thermal unit. So, to calculate the fuel consumption rate, we need to divide 689.270 British thermal unit per hour over 19,000 British thermal unit IBM, which we will get 36.3 IBM per hour. Go to the next question. The question is about the food compartment of the refrigerator shown in figure 6.23 is maintained at 4 Celsius by removing heat from it at a rate of 360 kJ per minute. If the required power input to the refrigerator is 2 kW, determine the coefficient of performance of the refrigerator and the rate of heat rejection to the room that houses the refrigerator. So when we analyze, firstly we need to find the coefficient of performance of the refrigerator. So coefficient of performance of the refrigerator is equals to Q over W, which we need to substitute the value of 360 kJ per minute over 2 kW in the formula, and we need to multiply it with 1 kW over 60 kJ per minute. We will get 3. Secondly, we need to find the rate at which heat is rejected to the room that houses the refrigerator is determined from the conservation of energy relation for cyclic devices, which we need to use the first law, energy conservation for cyclic devices. So, we need to use the formula that given and we need to substitute the value of 360 kJ per minute plus 2 kW multiplied with 60 kJ per minute over 1 kW, and we will get 480 kJ per minute. The energy removed from the fridge and energy used by the fridge become heat released to the room, showing energy transformation but no loss.